breaking a bond. But here you need a molecule to be a electron acceptor. A molecule which is a good electron acceptor, you can see this. That means a molecule which has a lowest unoccupied molecular orbital is a very good molecule to accept electrons and form a radical anion. So that means if I have a benzophenone can take an electron and form a benzophenone radical anion by just a simple addition of electrons or single electron transfer addition to the benzophenone can form this type of radical anion. Similarly, if the charge is positive, then we can call those as organic radical cations. This is one of the most earliest known radical cation and known as Wooster's blue. Wooster's blue. This is really a very deep blue colored radical cation. And there are multiple types of radical cations which are known. You can see all these structures. You can see this naphthalene radical cation. This is a pyridine based radical cation, right? Many types of radical cations are nowadays known. This is one of the most interesting radical cation. It is called the tetrathiafulvalene, TTF in short. TTF radical cation. This is very interesting because this was reported to be also a superconductor. This can form superconductors, and this was reported around 1970s to form organic superconductors around critical temperatures of around 10 to 15 K. So this is very interesting, and you can now easily imagine that why radicals are so important. Radicals are important because this can be conductive, this can be superconductive, it can show conductivity like metals, like silver, copper, very high conductivity. It can also be applied as superconductors. Apart from that, organic radicals can be controlled to form reactions for catalysis, many applications. So to form an organic radical cation, we must have this condition that it must be a good donor. So that means NMe2 phenyl NMe2, the starting molecule, the precursor, is a very good donor, has a high lying HOMO. So that means a good electron donor can form a radical cation. A good electron donor must have a high lying HOMO. That is it's very well known, because as you are putting more and more electrons to a molecule, the HOMO will rise, right? And then its oxidation potential is favorable. That means it can lose an electron and form a radical cation. Similarly, as I told you, in the radical anion, its reduction potential must be very suitable to accept an electron. So radical cations are formed from the precursor by losing an electron, and radical anions are formed by gaining an electron from the precursor. That is the major difference. So I quickly show you that how we have survived and how it is so important, how radicals uh, being so free to react can actually be uh, tamed or be controlled by other reactions or molecules which are present or vitamins which are present in our skin or tissues that can take care of these radicals and make us protected and keep us protected. And that is one of the example which I'll give you in the very beginning. Any one of you, can you tell me which is the example I'll be giving?
Triphenyl.
Where a vitamin helps us to protect from free radicals.
NTS. बोल दो जोर
And that is called the vitamin E. So how vitamin E is extremely useful to remove harmful radicals? So first let us see the structure. Let us see that what it happens. So that means that in our human tissues are made of molecules that are susceptible to homolysis in intense light. That means intense light is solar light, sunlight, UV light coming from the sunlight. And this, our body has found out some sophisticated chemistry, that means a mechanism to protect us from these reactive radicals. And vitamin E plays an important role in taming these radicals, that means controlling the reactivity of these radicals by abstraction of hydrogen. How it does it? That means vitamin E has some phenolic hydroxyl groups. As you may know that resveratrol and all these type of antioxidants also play this type of role, right? By abstracting the hydrogen radicals and produces a relatively stable radical that is not that harmful and that is stable in our body. So it does not lead to further reactions because radicals are free to react and react, forming chain of reactions. So that's the reason that vitamin E is so useful, and we generally know that we protect our skin when we go to the sunlight, right? Intense sunlight, particularly in the afternoon, after 10 o'clock, right? In the intense afternoon, we protect our skin by using UV protective lotions, right? Having vitamin E, zinc oxide, and many other chemicals. So let us see the structure of vitamin E. As I told you, this is type of moieties which are present also in antioxidant. So this is the critical moiety, this phenolic OH group in the vitamin E, and this is what is important to react with the radicals. So consider a dangerous radical like this, alkoxyl radical, which can initiate this type of a reaction. Remember that in radical chemistry, we will be showing arrows, half arrows. Okay, we don't use a full arrow for this type of a reaction from a radical. So this reactive radical can abstract this hydrogen, and then this forms a ROH type of a compound. This is a diamagnetic species, stable species, but then this is a radical species. But then this radical, you can easily imagine, this spin can now delocalize over this ring, and this actually makes this vitamin E based radical much more stable, and that's the reason it does not undergo further reactions, and that's the reason it protects our skin further under much more stressful conditions. So now let us go into the homolysis versus heterolysis process in bond breaking. As you know, we can make a homolysis type of a reaction by breaking hydrogen chloride molecule beyond 200 degrees centigrade, and that can form a H dot and a Cl dot. These are both are free radicals. But then we cannot break this HCl in the gas phase and form a ion. That means H plus or chloride minus. And this would have been a heterolysis of HCl. This is impossible to carry out. That means a heterolysis of HCl is impossible, but on the other hand, HCl can be broken, HCl gas molecule can be broken beyond 200 degrees centigrade by a homolysis process to form a H dot and Cl dot. Now I will ask you that why this reaction is not favorable. Can you tell me, can you make us understand? Any one of you, can you guess that why this reaction is so difficult to attain? That means the formation of the ions so difficult. Because HCl is solvated, you want to say?
The ions which are generated are being stabilized by solvations. So if solvent is not there, then it is unstable.
So actually, if it would have formed, if the reaction would have formed, then your ion pairs, this H plus and chloride minus would have solvated. You are very right. But then this reaction does not happen. It is impossible to carry out this reaction. In gaseous phase, remember, I am not saying in the solution phase. Please remember this. I am saying in the gas phase. Of course, in solution phase, it will ionize, as we know. In solution phase, it will ionize and we know that it will get solvated. But in gas phase, why this reaction is so difficult to do? And it is actually impossible to carry out this
Isolation of
reaction
H
in the gas
positive ion
phase.
is very difficult in gaseous phase. Its proton cannot isolate it in gaseous phase.
Any one of you?
H positive ion is not possible in gaseous phase. Tell me.
Exactly, very nice answer. The bond dissociation energy of HCl is very, very high, extremely high, and it is almost like 1400 kilojoules per mole, which we cannot attain before decomposing HCl. So that means this reaction is impossible to carry out, right, under the conditions which we can attain. That's the reason HCl can, in the gas phase, we can actually dissociate in a formation of the free radicals, but this reaction is absolutely impossible because of the very, very high bond dissociation.